Welcome to problem solving session number 7. In this problem solving session, we are going to solve problem based on what we have learned in the last 3 previous classes. The first problem that we are going to do is this. For the Cooper pair box, the below plot for eigenvalues E versus the parameter Ng is given, and you are asked to show that the point A and B in the plot correspond to the eigenstates that is given as a superposition of antisymmetric and symmetric superposition of the charge state n is equal to 1 and n is equal to 0. So we have to show it by doing some calculations. To do that, let us proceed as follows. We'll first write down the Hamiltonian, and we have already written down the Hamiltonian for this Cooper pair box when we operate it around the point Ng is equal to 1/2, and this is the Hamiltonian we wrote in our lecture classes. 4EC delta Ng minus Ez by 2 minus Ez by 2, and here we are having minus 4EC delta Ng, and we can immediately get the eigenvalues as E is equal to plus minus square root of Ez square by 4 plus 16 EC square delta Ng square. Okay, now at delta Ng is equal to 0, that means when we are taking Ng is equal to 1/2, that means we are going to have the energy eigenvalues as plus minus Ez by 2. Okay, now let's find out the eigenstates. In fact, I hope you are getting it why we are doing that, because delta Ng is equal to 0 at this point. This is the degeneracy point here. At this point, as you can see here, delta Ng is equal to 0. Now this point A correspond to the eigenvalue E1 is equal to plus Ez by 2. That refers to the point A in the plot, and let me denote the eigenstate as kth E1, and let's say kth E1 is its elements are column vector, we denote it, and then elements are say alpha 1 alpha 2, and we know how to find out the eigenstate just by taking this matrix Ez by 2, okay, minus Ez by 2, and here 0 because delta Ng is equal to 0. So this is the Hamiltonian we are considering because delta Ng is equal to 0. So the diagonal elements are 0 here, and we just need to solve this eigenvalue equation, eigenvalue matrix equation, and eigenvalue is plus Ez by 2, alpha 1 and alpha 2 are the eigenvector, and if you just do the calculation from here, you can immediately see that alpha 2 by alpha 1 is equal to minus alpha 1 by alpha 2, and that means you can write that alpha 2 is equal to minus alpha 1, right? And this means that this kth E1, you can write it as, you can take alpha 1 is equal to 1, then alpha 2 is equal to minus 1, and you have to take the normalized state vector. That means this eigenstate has to be normalized, so this is the normalization factor. Now this I can write as 1 by root 2, and I can write it as 1 0 minus 0 1, and if I now define n is equal to 1 as 1 0 and n is equal to 0 as 0 1, then I can write this state vector, this eigenvector corresponding to the point A as 1 by root 2 kth n is equal to 1 minus kth n is equal to 0. Similarly, we can now work out the eigenvalue equation for the eigenvalue is E2 is equal to minus Ej by 2, and that corresponds to the point B. And this eigenstate, let me refer as E2 is equal to say beta 1 beta 2. Okay, then again the same trick, you are going to get the eigenmatrix. This Hamiltonian is this minus Ej by 2, 0 here, and here we have this eigenvector as beta 1 beta 2, and eigenvalue is minus Ej by 2. Here you are having beta 1 beta 2, and this going to give you beta 2 by beta 1. Very trivially you can see that beta 2 beta 1 is equal to beta 1 beta 2. That means you are going to have beta 1 is equal to, or beta 2 is equal to beta 1, and that means you can take Kate E2, which refers to the point B. You are having, you can take beta 1 is equal to 1, then beta 2 is also going to be equal to 1, and because of the normalization you are having 1 by root 2 there, and this you can write it as 1 by root 2, you can write it as 1 0 plus 0 1, and by definition we have that E2 is Kate E2 is equal to 1 by root 2, and 1 0 is represented as the charge state n is equal to 1, and plus you are having n is equal to 0, right? So this is what was asked, and this refers to the point B in the plot. Now let us do the second problem. In this problem, you have to show through explicit calculation that this particular operator n cap minus nz is equal to 1/2 sigma x, where nz is equal to 1/2 for a Cooper pair box. In order to do this problem, we have to choose the basis vectors judiciously, and because we are focusing around nz is equal to 1/2, so let me take the excited state and the ground state as this, because we have already seen from the previous problem that at this point nz is equal to 1/2. Our excited state, this particular state which was referring to the point A in the previous problem, this we can take it as our excited state Kate E, and which is equal to 1 by root 2. It's a antisymmetric superposition of n is equal to 1 and n is equal to 0, and this particular point refers to the say ground state Kate Z, and that is the symmetric superposition of the charge state n is equal to 1 plus n is equal to 0. Now if we choose Kate Z and Kate E as our basis state, then I can write, let me write this operator n cap minus nz as say n cap, and this I can write just because this reason we know that any operator I can express it in this form Kate I bra I m Kate j bra j, where ij run from, ij can take the values, can take Kate z and Kate e. Okay, so utilizing this, let me write the full expression for n minus nz in terms of this basis vector, and that is going to be, we are going to have z m z Kate z bra z plus Kate e m, okay, Kate e bra e, and we'll have term like say z m e Kate z bra e plus Kate this e m z, will have Kate e bra z. So we have to find out all these matrix elements here, and that we can easily work out if we do it systematically. So to that, first let me find out what is mz operating on the Kate z, and this is equal to n minus nz. Okay, and we have Kate z is 1 by root 2. It's a symmetric superposition of Kate 1 plus Kate 0, and because n is a number state, so I can write n operating on 1 is going to give me ket1, n operating on ket0, this number operator operating on ket0 is going to give me simply 0, right? Utilizing this, you can immediately get from here, okay, let me write m is equal to n minus nz. Okay, so this is going to give me, from here you see, I am going to get n operating on ket1 and ket0, so this is going to give me ket1 plus 0, and nz is nz is a number here, it is 1/2. I will put 1/2 later. I will have minus mz 1/2 ket1 and minus nz ket0. Of course, I have a multiplicative factor of 1 by root 2 is also there. Okay, now from this I have n minus nz operating on ket z. If I put nz is equal to 1/2, then you will get it as you will get 1 by root 2. Here you will get 1/2 ket1 minus 1/2 ket0. If I put nz is equal to 1/2, this is what you will get. This I can write as 1/2 1 by root 2. I will have ket1 minus ket0. Okay, this is what I will get, and this guy is nothing but ket e. So I have 1/2 ket e. So what you see, you are ultimately getting n minus nz operating on ket z. This is going to give you 1/2 ket e. Similarly, again you can do the calculation for n minus nz operating on ket e. You can do the explicit calculations. Let me show you once again here. N minus nz, similar calculation. Now your ket e is antisymmetric superposition of ket1 and ket0. Ket was the, here first we have done it for ket which was the symmetric superposition of ket1 and ket0, but ket e is a antisymmetric superposition of ket1 and ket0. Again, doing this calculation, I am going to have 1 by root 2, the number operator operating on ket1 and ket0 is going to give me ket1 minus 0, right, minus nz ket1 plus nz ket0. Then if I put nz is equal to 1/2, then I will again get, in the similar way to the previous one, I will get 1 by root 2 ket1 plus ket0, and this quantity is nothing but ket-z. So I have 1/2 ket-z. So what I get? I get n minus nz operating on ket-e is going to give me 1/2 ket-z. So this way I can easily now find out, if I take the scalar product n minus nz z, and this one we had as 1/2 ket-e. So let me do it here. I have ket-z 1/2 ket-e. 1/2 is a number, so I have 1/2 the scalar product of the ground state and the excited state, and they are orthogonal to each other, so therefore it's going to give you 0. Now in the similar way, if I now take, say, e n minus nz ket-z, this will give me e. Here I will get, because of the fact that when this operates, you are going to get 1/2 ket-e. So therefore I will get here e here and 1/2 outside. So this is going to give me 1/2, and you will get z n minus nz e, and we know that n minus nz ket-e, this we have worked out, that is 1/2 of z. So therefore you will get here ket-z 1/2. So this is going to give you again 1/2, and this one n minus nz e, and because this part is going to give you 1/2 ket-z, so therefore you are going to get 0. So thereby you see that you are getting all the elements in the matrix. So I have then n minus nz is equal to m is equal to, I'll be left out with only 1/2 kg kt bra e plus kt bra z, and this I can express as 1/2 0 1 1 0, and this is nothing but the Pauli x component of the Pauli matrix, so I can write it as 1/2 sigma x cap. Alright, so thereby through this explicit calculation we are able to show that n cap minus nz, when nz is equal to 1/2, it gives you 1/2 sigma x. Now in this third problem, you are asked to show that the voltage operator V cap can be written for a single mode as this expression. Let's do that. It's a easy problem and it's very short also. Very simply you can show it. So to do that, you know that the voltage is nothing but the time rate of change of the magnetic flux. You know it from your elementary physics. Now we have in the quantum mechanical domain, this voltage is going to be an operator. Similar is the case with the flux operator, flux. So d phi cap dt. And we have this flux, magnetic flux operator, we have written it in terms of the 0-point fluctuation of the magnetic flux into A of t plus A dagger of t. Okay, and because we know that this annihilation operator evolves in time according to this expression, A of 0 e to the power minus I omega t, and A dagger of t is equal to A dagger of 0 e to the power plus I omega t. So you can immediately get that A dot t is going to be equal to minus I omega A of 0 e to the power minus I omega t, right? And this is going to give you, we can simply write it as minus I omega A of t, alright? And similarly you can write A dagger dot, time derivative of this creation operator would be plus I omega A dagger of 0 e to the power plus I omega t, and this you can write it as I omega A dagger of t. So magnetic flux, if you take the time derivative, this is going to give you time rate of change of the magnetic flux operator is going to give you phi z pf A dot of t plus A dagger dot of t, and this we have worked out. So you can get that this would be nothing but I omega phi zpf A dagger minus A. Okay, and this means this voltage operator can be written as I omega phi zpf A dagger minus A. And in the lecture class I have just written it in this form without giving you any explanation. That's why I am doing this problem here. Let us now work out this problem. Obtain the following equations for Josephson junction, and these equations that I am writing here we actually discussed in lecture number 25, that means in the last lecture. So let us work these equations out doing explicit calculations now. To do that, we know that this Josephson junction is nothing but two superconductors placed adjacent to each other, and they are separated from one another by a thin junction, thin layer, thin insulating layer. So this is superconductor 1 and this is superconductor 2, and there is a voltage is applied between these two electrodes. And the model that was used was this, the Couples-Schrödinger equation, I h bar delta psi 1 delta t is equal to E1 psi 1 plus k psi 2, where k is the coupling, and I h bar delta psi 2 delta t is equal to E2 psi 2 plus k psi 1. This we have written in the last class, and psi 1 is equal to rho 1, which is the density of Cooper pairs in the first superconductor. I theta 1 is the phase in the first superconductor. Psi 2 is similarly rho 2, e to the power I theta 2. Rho 2 is the Cooper pair density in the second superconductor. Theta 2 is the corresponding phase. So let me now take a time derivative of delta psi 1, and this is what I'll get. Delta psi 1 delta t is equal to 1/2 1 by root over rho 1, and you will have here rho 1 dot e to the power I theta 1 plus I square root of rho 1 theta 1 dot e to the power I theta 1. Okay, so this is what I will get, and from the second part I will get delta psi 2. Similarly, I can find out time derivative of psi 2. That is going to give me 1/2 1 by square root of rho 2 dot e to the power I theta 2 plus I square root of rho 2 theta 2 dot e to the power I theta 2 dot. Okay, so this is what I will get. Now from this equation 1, I can write I h bar 1 by putting the value of delta psi 1 delta t. Actually I will get 2 rho 1 dot e to the power I theta 1 minus h bar square root of rho 1 theta 1 dot e to the power I theta 1 is equal to, I am putting that in these coupled Schrodinger equations. Now I am putting delta psi 1 delta t in this first equation, and on the right hand side I will get E1 square root of rho 1 e to the power I theta 1, okay, plus k root rho 2 e to the power I theta 2. And if you do the actually algebra, then let me write down the final expression what you are going to get out of all these things. If you do that carefully, you will get I h bar rho 1 dot minus twice h bar rho 1 theta 1 dot is equal to twice E1 rho 1 plus twice k square root of rho 1 rho 2. And actually let me show you all the steps so that rather than writing the final expression, let me do it from here. Okay, next step I will get as I h bar rho 1 dot minus twice h bar rho 1 theta 1 dot, okay, is equal to twice E1 rho 1 plus twice k square root of rho 1 rho 2 e to the power I theta 2 minus theta 1. Now this guy theta 2 minus theta 1 is delta, right? Therefore I can now write it as I h bar rho 1 dot minus twice h bar rho 1 theta 1 dot is equal to twice E1 rho 1 plus twice k square root of rho 1 rho 2 e to the power I delta. I can write it as cos delta plus I sin delta. Okay, what I am going to do next, I am going to equate the real and the imaginary part on both sides. Let me write here, equating real and imaginary parts on both sides, imaginary parts on both sides of the equations. I will get this set of equation h bar rho 1 dot is equal to 2k square root of rho 1 rho 2 sin delta, and from the next one the imaginary part is going to give me twice h bar rho 1. In fact, the real part is going to give me minus twice h bar rho 1 theta 1 dot. Okay, please look at the both sides carefully. The imaginary part is going to give me, this is going to be equal to twice E1 rho 1 plus twice k square root of rho 1 rho 2 cos delta, and from here I can write it in the more simpler form as rho 1 dot is equal to 2 by h bar k square root of rho 1 rho 2 sine delta, and theta 1 dot is equal to minus k by h bar square root of rho 2 by rho 1 cos delta minus E1 by h bar. Now from the second equation you can do the similar calculation. So from equation number 2, that means from this part, from this equation you have to put it here in this Schrodinger equation. On the left hand side if you put that, and psi 2 also you put it as square root of rho 2 e to the power I theta 2. Then if you do the algebra similar to the one that I have done, I am giving you the final expression here, so that is easy to understand. You will get I h bar rho 2 dot minus twice h bar rho 2 theta 2 dot is equal to twice E2 rho 2 plus 2k square root of rho 1 rho 2, and here you will get again e to the power, this time you will get e to the power minus I delta, so you can write cos delta minus I sine delta. Again comparing the real and the imaginary parts, you are going to get rho 2 dot is equal to minus twice h bar k square root of rho 1 rho 2 sine delta, and theta 2 dot is equal to minus k by h bar square root of rho 1 by rho 2 cos delta minus E2 by h bar. Now you have to take, if I now take that this E1 is equal to E2 is equal to charge of the electron into the voltage, that is because this energy, then I can rewrite all this equation in this form. Rho 1 dot would be equal to 2 by h bar k square root of rho 1 rho 2 sine delta, and rho 2 dot is equal to minus 2 by h bar k square root of rho 1 rho 2 sine delta, and theta 1 dot is equal to minus k by h bar square root of rho 2 by rho 1 cos delta minus QE into voltage divided by h bar, and theta 2 dot is equal to minus k by h bar square root of rho 1 by rho 2 cos delta plus QE voltage divided by h bar, and here delta is equal to theta 2 minus theta 1. So these are the desired set of equation we are asked to derive. Let us now consider this problem. The general charge qubit Hamiltonian is given in this form. Using the Fourier transform pair, you are asked to show that the Hamiltonian can be re-expressed in this form. Okay, let's do it. To do that, we will focus first on the Josephson energy term in the charge qubit Hamiltonian. We will focus on this term. This term I can write as Ej cos delta, the phase operator, as Ej by 2 e to the power I delta cap plus e to the power minus I delta cap, and it's quite obvious. Now e to the power I delta cap is a quantum mechanical operator Therefore, I can write it as e to the power I delta cap, and then I can sandwich this identity operator here from the number basis, Cooper pair number basis, and goes from minus infinity to plus infinity, ket n, bra n, because you know that this guy is nothing but the identity operator. Okay, so now this one I can now write as n goes from minus infinity to plus infinity e to the power I delta cap operating on this ket n, and we are having this. So first of all, we have to find out what is this quantity. If I operate on this number ket by this operator e to the power I delta, what we are going to get. To do this, let me now write e to the power I delta as in this form, because again I can introduce this identity operator in terms of this phase. Let me just write it first. I have 1 by 2 pi 0 to 2 pi this phase operator ket delta bra delta d delta, and this guy is identity, and this delta is a continuous operator, so it takes value from 0 to 2 pi. And if I operate on this ket delta, you can actually very easily show, because if I expand this e to the power I delta cap, I have 1 plus e to the power I delta plus, and you will get all other terms. But because for every phase I have only, it's the wave function has to be single valued, these values of delta are unique, it has to be diagonal, I mean to say. That's the reason you are going to get delta ket delta, where delta is a number, and because of this you will get it as delta plus I delta ket delta and so on. In fact, this is amount to 1 plus I delta, okay, and ultimately, and so this is trivially e to the power I delta. This is just a number you are getting, so e to the power I delta is your eigenvalue now. Therefore, I have e to the power I delta cap. I can now write it as 1 by 2 pi 0 to 2 pi e to the power I delta ket delta bra delta d delta. So this is what now we are going to use in the next part. Here I now use e to the power I delta operating on this number ket n. I can have from this expression, I have 1 by 2 pi 0 to 2 pi, okay, e to the power I delta ket delta bra delta, and this is operating on this number ket n. I have d delta, and this I can write further as 1 by 2 pi 0 to 2 pi, okay, e to the power I delta. Let me take this integration here, and let me take this, but this part let me write carefully. This I can write because it is given. This one I have from my problem, Fourier transform pair. Ket delta I can express in terms of ket n. Utilizing this, I have to take the bra of ket delta, right? So therefore I am going to get here summation. Let me take m goes from minus infinity to plus infinity. I have e to the power minus I m delta bra m, and then from this I have already ket n, and this quantity you can easily see this is nothing but the Kronecker delta. So because I am using only this delta term, so let me write it simply like this. So this is my Kronecker delta mn, and that is going to be equal to 1 if m is equal to n, otherwise it is going to be 0. So utilizing this, I can write e to the power I delta cap operating on this ket n is going to give me 1 by 2 pi, okay, 0 to 2 pi e to the power I delta d delta ket delta, and from here I am going to have e to the power minus in delta, exploiting the property of the Kronecker delta, and I can then have 1 by 2 pi integration 0 to 2 pi, okay, e to the power minus I n minus 1 delta k delta d delta. This means I can write this whole quantity as number kit n minus 1, because this number kit kn we can now write as, this is, it is given in the problem, we can write it as 1 by 2 pi 0 to 2 pi d delta e to the power minus in delta k delta. Okay, so we have e to the power I delta cap is equal to n goes from minus infinity to plus infinity e to the power I delta n kn bra n. This I can, because I already have worked out this part, right? So therefore utilizing that, I have n goes from minus infinity to plus infinity. Here I have n minus 1 and this bra n. This actually I can also write without loss of any generality, because n goes from minus infinity to plus infinity. This I can write it as k10, and this I can write it as bra n plus 1. Similarly, you can show that bra n operated by this operator minus I delta cap, this is going to give you bra n plus 1. Alright, then therefore we get Ej cos delta cap, that is equal to Ej by 2 e to the power, this already we wrote, right, e to the power I delta plus e to the power minus I delta cap. This I can, okay, let me write here clearly, Ej cos delta cap is equal to Ej by 2. Now I have e to the power I delta cap, that is n is equal to minus infinity to plus infinity e to the power I delta cap kate n bra n plus n is equal to minus infinity to plus infinity. I can here have, this is your k10, just identity I am putting, k10 e to the power minus I delta cap. Here actually I am doing nothing, just try to understand. Here I am putting one identity operator and here I am putting another identity operator, and this is a trick worth attempting, and this is what I have done here. Okay, so this results in Ej by 2, and here I am going to, already I have worked this term. Similarly you can have this term. You will get kate n plus 1 bra n plus kate n bra n plus 1. Okay, so this is what was required. By the way, we have to consider the first term also in the Hamiltonian, that was 4ec n cap minus nz whole square. Now because of the fact, this term let me consider, now because of the fact that this number operator has this property, n cap n is equal to n cap k10, so 4ec n cap minus nz whole square, I can now write it as 4ec n cap minus nz whole square. Then again putting this identity operator here, I have n is equal to minus infinity to plus infinity kate n bra n, right. This I can now write as, because this term is diagonal, so I have n is equal to minus infinity to plus infinity. I have 4ec n minus nz, because of the eigenvalue, this is what I am going to get, and I have here k10 bra n. Hence we have the full Hamiltonian now. H is equal to 4 EC n cap minus nz. This is the charge qubit Hamiltonian that is given to us, Ej cos delta cap. This I can now write as n goes from minus infinity to plus infinity. Okay, then I have here 4 EC n minus nz. These are numbers, eigenvalues. Then I have here k10 bra n, and from the second term I have Ej by 2 k10 bra n plus 1 plus k n plus 1 bra n. So this is what we got, and this is what was required. Let us now work out this problem, and I have promised you to do this problem in the lecture classes. To do this, let me first work out it step by step. First, let me work out this portion. Sigma x, that is the x component of the Pauli operator, a plus a dagger operating on the combined state of the atom and the field, and this sigma x is going to operate on the atom part, that is your kg, and a plus a dagger, which is coming from the harmonic oscillator, that is going to act on the number state ket n. Okay, and sigma x, when it operates on kg, it is going to give you ket e, and a plus a dagger when operate on ket n, a operating on ket n is going to give you square root of n minus 1, and a dagger operating on ket n is going to give you square root of n plus 1 ket n plus 1. Now, after having this, let me now take the scalar product with e n minus 1, and with this sigma x a plus a dagger zn, and we have already worked this part, so let me put the whole thing here. E n minus 1, this part I have ket e root over n minus 1, and I have ket e root over n minus 1 n plus 1, okay, square root of n plus 1, and ket n plus 1. So we will get ket e bra e, the scalar product of e, and then scalar product of n minus 1 n minus 1. We have a square root, n is also there, that's a number. So I have this from the first part, and from the second part I have ket e, a scalar product of e, and I have this scalar product of n minus 1 and n plus 1, and then multiplied by this number square root of n plus 1. Now, because of the fact that n minus 1 n minus, this is normalized, this is going to give me 1, this is also normalized, it's going to give me 1, this is normalized, but this guy are orthogonal, so this is going to give me 0. So therefore I will have simply square root of n. So finally we get e n minus 1 h bar z sigma x a plus a dagger zn is going to give h bar z square root of n, and that is what is required. Now let us do this final problem of this problem solving session. You are asked to discuss the Jaynes-Cummings model for the dispersive case, where the detuning, magnitude of the detuning is much greater than that of the coupling between the field and the atom. Then you have to find the energy eigenvalues of the JC Hamiltonian. And from the last lecture, we know that the Jaynes-Cummings Hamiltonian under the rotating wave approximation is h is equal to h bar omega a dagger a, which describe the field. Then we have this atom part, h cross omega atom sigma z plus 1 by 2, and then this coupling, field atom coupling term, h bar z sigma plus a, sigma plus is the atomic raising operator, and sigma minus, that is the atomic lowering operator. This is what we have. Now this Hamiltonian was written in the matrix form in this way. H is equal to, we have this matrix H cross omega or H bar omega n, H bar z square root of n, H bar z square root of n, and here we have H bar omega n plus H bar delta, where delta is the detuning and it is defined as omega atom minus omega. Okay, this Hamiltonian, we can easily find out the eigenvalues if I write in this form. I can write it as H cross omega n 1 0 0 1 plus I have 0 H bar z square root n, H bar z square root n, H bar delta. This I can further write, the first term would remain as it is, H cross omega n 1 0 0 1. This second term I can write as H bar delta by 2 1 0 0 1, and from the last part I have this, I can now write as, I have to add this part so that I get this term, the second term in the Hamiltonian. I have H bar z root n, H bar z square root of n, and here I have H bar z by 2. Okay, now if you look at this matrix, it should remind you about this matrix that we have discussed when we have discussed about general two level atom, and there we wrote this matrix, and we saw that the eigenvalues of this matrix can be very trivially written as plus minus square root of ex square plus ez square, and this feature now I can exploit, and I can now write down the eigenvalues for this part of the Hamiltonian, and that's going to be equal to square root of h bar delta by 2 whole square with this plus minus whole square plus h bar z square root of n whole square. So I can now immediately write down the energy eigenvalue of this Jens-Cummings Hamiltonian. So let me write it at E0. Don't get confused with this capital E I'm writing here. So from this part the eigenvalues is h cross omega n. From this part the eigenvalues are h bar delta by 2. So I have h cross omega n, h cross delta by 2, and I have plus minus square root of, I can take my h bar outside, then I will have z square n plus delta by 2 whole square. Okay, so this is what I am going to have. Now we are given, basically we are assuming that this detuning parameter delta magnitude is much greater than this coupling parameter z, and this is the dispersive case. Then I can expand this particular term using Taylor's expansion. So let me do that first. Z square n plus delta by 2 whole square, this we can now write as delta by mod delta by 2. If I take mod delta by 2 common, delta by 2 whole square as common, and then I have here 1 plus z square n divided by delta by 2 whole square. Okay, this I can now write, let me write this here more clearly. Let me have z square n plus delta by 2 whole square square root is equal to mod delta by 2, and this square root term that I can expand into a Taylor series binomial expansion. Let me do it. 1 plus 1 half, I will have 4 z square n, okay, divided by delta square, and we'll have higher order terms. Those terms we can neglect because these terms are going to be smaller and smaller. So I will have my first term as mod delta by 2, then the second term is going to be z square n divided by mod delta. And if I take that detuning to be positive, delta is greater than 0, then I have my energy eigenvalue E plus would be h cross omega n plus h cross delta by 2 plus h bar delta by 2 plus h bar z square n divided by mod delta, and this is going to give me E plus as h cross omega plus z square by mod delta, okay, into n plus h bar delta. So this is the expression for E plus, and similarly I get E minus for the other term, E minus, because I have here this, square root of plus minus was there, this you see here. So we'll get E minus is equal to h cross omega n minus. Now that is because of the fact that, by the way, please be careful here, this plus minus sign is there. So here this plus minus sign is there. So because if I take the minus sign, then this term and this term, this h cross delta by 2 term is going to get cancelled out. So we are going to have E minus as h cross omega n minus h bar z square n divided by mod delta. This I can now write as E minus is equal to h bar omega minus z square by mod delta into n. So this is my E minus. So if you look at these two terms carefully, you see E plus corresponds to the excited energy state, the case basically then when the atom is in the excited state, and E minus corresponds to the case when the atom is in the ground state. So we can, to a good approximation, take that my energy eigenstate corresponding to E plus as ket E plus to be equal to atom in the excited state, and there is one less quanta in the field, and E minus, ket E minus as the atom in the ground state, and there is n number of quanta in the field. Now from this term where we have this h bar omega plus minus z square by delta n, you see here this plus term refers to E plus and minus term belongs to this energy eigenvalue E minus. In fact, from this you can make this conclusion that the field mode frequency, because omega is the frequency of the field, so when it is interacting with the atom, and after that when the field is getting, the radiation is getting emitted, generally this system is put in a transmission line resonator as we have discussed, and when this field mode frequency is measured, if you get the field mode frequency as omega plus z square by mod delta, that means the field frequency is upshifted, that means the atom is in the excited state, without measuring the atom, its atomic state, just by measuring the field mode frequency. If you find that the field mode frequency is upshifted, because this is going to be upshifted by this amount, then you can conclude that the atom is in the excited state E plus, it is going to be in energy level E plus. And if you find that the field mode frequency, these are called spectroscopic measurement, if the field frequency is found to be omega minus z square by mod delta, that means the atom is in the ground state, That means the atom has energy E minus. So if you find that the field mode frequency is downshifted, because initially the when it is entering into the resonator the field frequency was omega, so if you find the transmitted radiation, the microwave radiation, to have a lower frequency, then you can understand or conclude that the atom is in the ground state, and this you can do without even measuring the atomic state directly, atom measurement directly. And this is going to enable us to write an effective Hamiltonian. Because of this observation, we can write H effective as H bar omega plus z square by delta sigma z. I will explain it. A dagger A. Now this is the frequency of the field mode, that is transmitted field mode, and sigma z is equal to +1 if the atom is in the excited state, say E plus, and sigma z is equal to -1 if atom is in the ground state, that means it is in the energy level E minus. And the atom part, you can now write it as H cross omega atom plus z square by delta, and here you have this usual part sigma z plus 1 divided by 2. Now this particular part z square by delta is entering because the atom is getting coupled to the field. With this, let me conclude this section of superconducting circuits or superconducting qubits.